Welcome back. Today we're going to be talking about the intermediate value theorem. We're going to be going over 4 examples of multiple choice questions for the intermediate value theorem, and also 3 examples of long form questions for intermediate value theorem as well. So let's jump in. Okay, so first, really quick, what even is intermediate value theorem and what does it state? Well, basically, it states that if f is continuous on an interval from a to b, and k is any value between f of a and f of b, right? So k is somewhere between f of b and f of a, or between f of a and f of b, right? Depending on the order, right? Because we don't know if it's decreasing overall, if it's increasing, we don't really know what the deal is there, but either way, this will still work. Then there exists at least one c, so there exists some value of c that's an element of from a to b, where f of c is equal to k. Now let's also visualize this, because this may seem like a wall of text, this might seem really complicated, really confusing potentially, but actually I think if we draw a picture, it's actually showing something that isn't necessarily too challenging to understand, which is good news. All right, so for instance, I'm gonna draw something. So let's say here we have A and here we have B. So here's my interval. And let's say maybe it's decreasing. So we're gonna go here and then kind of come down, and then we'll stop here. And so as you can see, well, then this value therefore would be f of A, and this value here would be f of B, right? And basically what they're saying is there must exist some c, so some value somewhere in here that's c, between a and b, where f of c is equal to k, right? So basically what it's saying, since k is something between f of b and f of a, that means that if I, like let's say k is here, well then does there exist a c? Yep, there exists one right here. Let's say k was somewhere else, like let's say k was here. Well, then, does there exist an f of c? Yep. Or, does there exist c? Yeah, absolutely. Right? Because in order to get from here, like from all the way up here down to here, then we have to have some steps in between, right? We can't just do a jump because of the fact that f is continuous from a to b, including a and b there as well, right? And so I challenge you to find any point, right, any k between here that does not have a valid c, right? And you can't do it because that doesn't exist, because the that just wouldn't be possible given that it's continuous along that interval. So that's just my basic explanation there for what is intermediate value theorem and what does it state. Next, let's actually get into some of these questions and talk about it. Okay, so the first one here says that for which function does the IVT, the intermediate value theorem, guarantee a root in 0, 2? All right, so what does this mean? It means in somewhere in from 0 to 2, where do we have a root? So where do we have, in other words, f of x equaling 0? Well, let's try the first one and see if it's accurate or not. So first we have to find f of 0. F of 0 would be 0 squared minus 3 times 0 plus 2, which is 2. And then what about f of 2? F of 2 is equal to 2 squared minus 3 times 2 plus 2, which is equal to 4 minus 6 plus 2, which is equal to 0. And so therefore, because we did get a 0 there, this would be the answer, right? Because f of 2 is 0, right? And so therefore, that value there would be 2 comma 0. That would get us our root. And so there we go, we have it. Or really any values here that we would get out from f of a and f of b, that where one's positive and one's negative, or one's 0 and one isn't, would work, because we just have to have a 0 between them for this to work. Now, what about 1 over x minus 1? I know we already found the answer, but let's show why the other ones are not correct. Well, if we did f of 0 here, we would get 1 over negative 1, which is negative 1. And then for f of 2, we would get 1 minus 2, 1 over 2 minus 1, which is 1. And so on the surface, it looks like, oh, well, couldn't it be b? Because 0 is between these values, so at some point we would have to hit 0. However, keep in mind that's only true if it's continuous from 0 to 2. And is that true? Well, no, it isn't, because recall that when we have something like this, it's not going to be continuous all the way through. Okay? So since it doesn't have that principle of continuity, then B cannot be the answer for that reason. Whereas for A, going back to A, this is a quadratic, right? A quadratic is just continuous everywhere, and so that's not something we have to worry about as to whether or not it would be continuous from 0 to 2, because it's continuous anywhere or everywhere anyway. Because recall that this is discontinuous at x equals 1, right? If I plug in 1 here, then it's undefined, so it's discontinuous somewhere on our interval, and so that doesn't work, even though this other condition is met. Now, what about the third one, tan x? Well, this is also has the same problem, right? This is not continuous everywhere from 0 to 2, right? Recall that this is not continuous at, let's see, where might it not be continuous? This wouldn't necessarily be continuous at like pi over 2, for example, which is in the interval. And so therefore, the intermediate value theorem can't apply since the hypotheses aren't maintained there. And then for this one, this is also a quadratic, and so this will be continuous everywhere and therefore continuous from 0 to 2. But this does not guarantee a root, because if we plug in f of 0 and f of 2, notice that here we get 1, and here we get 2 squared plus 1, which is 5. And so this guarantees us that we'll have something between 1 and 5, but not necessarily a root. And in fact, if you know how to, I'm sure you probably learned how to graph this years ago. If you do know how to graph this, right, you'll remember that, oh no, actually there isn't a 0, right? Now, all we know from intermediate value theorem, setting aside what we knew previously, all we know for sure from intermediate value theorem specifically is that it's not guaranteed to have a root. From other stuff, I'm sure you know that there definitely isn't one, right? But A, based on the intermediate value theorem, says that there is guaranteed to be a root between 0 and 2, based on what we learned there. All right, let's try another one. Okay, so the next one says the intermediate value theorem can be used to prove that x cubed minus 4x plus 1 equals 0 has a solution in 0, 1, 1, 2, both A and B, or neither A nor B. Okay, so first off, where is this continuous? Well, x cubed minus 4x plus 1 is a polynomial function. And so it is going to be continuous everywhere. And so in terms of it being continuous on both of these intervals, that condition is met. Now the question is, in these intervals, do we have to guarantee pass 0? That's the question. So in order to figure that out, let's let f of x be equal to x cubed minus 4x plus 1. And we're going to punch in 0 and 1, and then 1 and 2 to find out if f of 0, f of 1 does have a guaranteed 0 in somewhere in there, or if it doesn't. Okay, so f of 0 would be 1, and f of 1 would be 1 cubed minus 4 times 1 plus 1, which is 1 minus 4 plus 1, which is negative 2. And so my answer is yes, absolutely, right? That the interval from negative 2 to 1 does indeed have 0 in there, right? It does pass through 0. And so the answer definitely is A. So therefore, we can eliminate the answer being neither A nor B, because definitely A is a correct answer, and we can also eliminate it being only B. But the question is the answer potentially both of A and B? Let's think about that. So let's do f of 2. So f of 2 would be 2 cubed minus 4 times 2 plus 1, which is 8 minus 8 plus 1, which is 1. So if we do from f of 1 to f of 2, in this case, what happens? We get negative 2 to 1, right? We get the same interval again, which means yes, it's going to work for both A and B. Now, even if we didn't get the same interval again, the point is that we got something that had 0 in it, right? 0 is part of this, right? Somewhere between -2 and 1 is indeed 0, and so therefore there is guaranteed to be a root between 0 and 1, and then another root between 1 and 2 in this situation of this cubic function. All right, and let's try the next one. This one's more of kind of a theory question, and it asks, which condition is not required for IVT intermediate value theorem? The first one says function must be continuous on from A to B, so that is absolutely a requirement, so that one will not be the correct answer because that's true. K must be between f of A and f of B. So once again, if we go back to the beginning part of the video where I talk about what the intermediate value theorem states, we know that K does have to be between f of A and f of B. It could be including those values, that's fine, but it does have to be between, so this would be true. C says the function must be differentiable on A comma B. Now that's not necessarily the case. It doesn't have to be differentiable. It just has to be continuous. So even if there's corners and cusps or things like that, that wouldn't be differentiable but would be continuous, that's totally fine for intermediate value theorem. And so C would be the answer because the original definition for intermediate value theorem didn't say anything about differentiable. It didn't mention derivatives at all whatsoever. And then D said the domain must be a closed interval. And yes, that is true. The domain absolutely must be a closed interval as well. It cannot be an open interval. All right, so that's that one. Let's try another. This next one will be our last multiple choice. Then we're going to move on to some free response questions as well. If f is continuous on 1 comma 5, with f of 1 being -2 and f of 5 being 10, the intermediate value theorem guarantees, let's see, A says it guarantees that f of c equals 0 for some value from 1 to 5. Well, yes, this would be true, because keep in mind that f of 1 was -2, so basically the function starts at -2, right? And then it goes all the way up to 10, right? F of 5 is equal to 10, and f of 1 is equal to -2. So somewhere when c is between 1 and 5, at some point here between 2 and 10, we do indeed have to get to 0 at some place. And so yes. B says that f of c must be 4 for some value between 1 and 5. And yes, that's also true because again, 4 is also between -2 and +10. It's also somewhere there. And so this is also true. And so my answer for this one is going to be B, that both, or it's going to be C rather, sorry, that both A and B are indeed correct because we checked those numbers, we checked that they were between the bounds we needed them to be, and they both were. In fact, any number between -2 and 10, had they put it here for f of c equals any number between -2 and 10, that would have been correct. Any number outside of the interval that no, we could not have guaranteed that that was the case. All right, let's move on to the next question. All right, so let's move on to the first free response question. It says, prove that the equation cosine of x equals x has at least one solution in 0, comma, pi over 2 using the IVT and show all your work. Okay, so first we need to actually express cosine of x equals x in a suitable fashion for the intermediate value theorem. So I'm going to do that by having 0 on one side and everything else on the other side. So I'm going to express this as 0 is equal to cosine of x minus x. And then I'm going to define my function as f of x must equal to cos x minus x. So now I need to show that there is at least one solution, that we can get, that we're going to end up getting something that encompasses 0 when I plug in my bounds, when I plug in 0 and when I plug in pi over 2. So let's do that. So f of 0 is going to be equal to cosine of 0 minus 0. Now, what's cosine of 0? That'd be 1, right? So that's going to be 1 minus 0, which is 1. Then I'll do the same thing with pi over 2. So what is f of pi over 2? That'd be cosine of pi over 2. All right, and what is cosine of pi over 2? Well, cosine pi over 2 would be 0, so we would just get 0 minus pi over 2, which is just going to be negative pi over 2. And so, therefore, basically it's saying that there will be a solution between negative pi over 2 and 1. And 0 is included in this. And so I would say that since 0 is included in from negative pi over 2 to 1, therefore, by the intermediate value theorem, there is at least one solution, right? There is at least one solution in there. And there we go. All right, so the next one says, let f of x equal to x to the power 5 minus 3x minus 1. Show that f has at least one root in 1 comma 2, and justify your answer using intermediate value theorem. So first things first, we know that f of x is continuous on 1 comma 2. Now, how do we know that? Well, it's continuous everywhere, right? This is just a regular polynomial function, right? This is a quintic function, and so, or a quintic polynomial, I should say. And so, therefore, it is continuous from 1 to 2, and therefore continuous, right? It is continuous everywhere, and therefore is continuous from 1 to 2. So then what I'm going to do is I'm going to find f of 1 and f of 2, and we're going to see if 0 is included in that, because if 0 is included somewhere there, then that means that there is at least one root. So f of 1 would be 1 to the power 5 minus 3 times 1 minus 1, which is 1 minus 3 minus 1, which is negative 3. And then we're going to have 2 to the power 5 minus 3 times 2 minus 1, which, let's see, 2 to the power 5, well, that'd be 32. So 32 minus 6 minus 1, which is going to be 25. And so therefore, we know that there is a 0 somewhere from negative 3 to 25. And so because there is a 0 somewhere in there, there is at least one root. In our original interval from 1 to 2, right? Because we got a negative and a positive, and so 0 is a part of that. All right, let's do one last one. All right, the last one says a function g is continuous on negative 2 comma 2, with g of negative 2 being negative 5 and g of 2 being 13. Can we conclude that g of c is equal to 0 for some c from negative 2 to 2? Explain why or why not. So in this case, yes, because all the properties of IVT, of intermediate value theorem, are met, right? So I'm going to say yes because the IVT hypotheses are met, right? Because first of all, we know that G is continuous on negative 2 to 2 because it says so in the question. We also know that G of negative 2 is negative 5 and G of 2 is 13. And because 0 is an element between and somewhere in the range of negative 5 to 13, right? It's somewhere in that range. Therefore, that does tell us that for some, that G of C equals 0 for some C, right? There must exist some C for which that is the case. Now, we don't know what that C is without knowing more info, but yes, intermediate value theorem does say that this must be the case. As always, if you have any questions, feel free to leave those in the comment section, and we'll see you for the next one.